It is the only physical theory of universal content concerning which I am convinced that it will never be overthrown. Now, those are the exact words of Albert Einstein. And let's be honest, when arguably the greatest mind of the 20th century tells you a scientific framework is literally invincible, you know you're looking at something profoundly important. We're talking, of course, about thermodynamics.
Welcome to this explainer. Today, we're unlocking the secrets of thermodynamics. Now, I know the word itself can sound a bit intimidating, but at its core, it's really just the study of how energy transforms in the physical world. I mean, think about it. How does the chemical energy in your cooking gas actually turn into the heat that boils water for your pasta? Or how does fuel in an engine transform into the mechanical work that physically drives your car forward? These aren't just dry chemistry questions. They're the fundamental rules that govern exactly how our entire universe operates. So let's see what happens when we break them all down.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with the thermodynamic universe, look at the types of systems, discuss the currency of change, hit the first law, and finally we'll wrap up by introducing enthalpy.
So part 1, the thermodynamic universe, and zooming in on the system.
I want you to imagine the absolute vastness of space. We're talking galaxies, stars, the whole shebang. Now, mentally zoom all the way into a single tiny beaker sitting on a lab desk. That beaker is what we call our system. It's simply the specific, defined part of the universe where we're making our observations. Everything we actually care about tracking right now, the molecules, the chemical reactions, the heat, it's all happening right there. And it's separated from the rest of the world by a boundary, which in this case is just the glass walls of the beaker.
Now, if that beaker of reacting chemicals is our system, what is literally everything else? Well, that would be the surroundings. The surroundings include the desk, the air in the room, the scientists watching, and yes, the rest of the cosmos. But for all practical purposes, the surroundings are really just the immediate neighborhood of the system, the space that can actually physically interact with our little beaker.
So the absolutely crucial takeaway here is this beautifully simple equation. In thermodynamics, the entire universe is just the system plus the surroundings. That's it. This incredibly simple division is what lets us easily track matter and energy as they cross that boundary.
Moving on to part 2, types of systems and the rules of exchange.
Now that we've established our boundary, we have to ask what exactly is allowed to cross over it. Notice how these arrows brilliantly illustrate the 3 possible scenarios. In the first setup, both matter and energy are flowing totally freely. In the second, only energy is moving, and in the third, absolutely nothing gets in or out.
Let's ground these abstract ideas in some real-world examples. An open system exchanges both energy and matter with its surroundings. Think of an open cup of hot coffee. Steam escapes, so it's losing matter, and it cools down, so it's losing energy. A closed system, on the other hand, exchanges energy only. Imagine a sealed steel vessel. No chemicals can escape, but those steel walls can definitely radiate heat out into the room. Finally, an isolated system exchanges neither. The closest real-world example we have to this is a high-quality thermos flask. It's perfectly sealed and heavily insulated, keeping the hot water trapped inside, right along with all of its heat energy.
All right, let's head into part 3, the currency of change, or as I like to call it, the energy bank account.
When these systems interact with their surroundings, what they're really doing is exchanging energy. And honestly, it's incredibly helpful to think of a system as having its own cosmic bank account. The total balance of that account is called internal energy, denoted by the letter U. It is the absolute sum of all the energy hiding inside: chemical bonds, electrical energy, mechanical movement, you name it. Now, we can't easily measure the absolute total sitting in that account, but we can definitely track the deposits and the withdrawals.
There are 2 main ways to make those deposits or withdrawals, basically to change that internal energy balance. The first is work, represented by a lowercase w. This is mechanical, like physically compressing a gas with a piston. The second is heat, represented by Q. This is energy transfer driven purely by a difference in temperature, like taking our beaker and placing it onto a hot stove. So both work and heat are just different currencies used to alter the system's internal energy account.
This equivalence was famously proven way back between 1840 and 1850 by J.P. Joule. He actually designed an experiment where he churned water with a set of rotating paddles, basically doing mechanical work on the water. And he found that doing work raised the temperature of the water in the exact same way that heating it over a flame would. Joule showed us that whether you deposit cash or a check, it goes into the exact same internal energy bank account.
That brings us to part 4,
the first law, which is all about balancing the cosmic checkbook.
Let's see how this builds and formalize that math to balance the checkbook. Step 1, we measure the mechanical work done, W. Step 2, we measure the heat transferred, Q. And step 3, we literally just add them together. The total change in internal energy, which we call delta U, is simply equal to Q plus W. That's it. The total change to the system's energy is just the sum of the heat added to it and the work done on it.
Now, what you're looking at with that simple little equation is actually the mathematical statement of the first law of thermodynamics. You probably know it by its more common, everyday name, the law of conservation of energy. It tells us that energy can neither be created nor destroyed. So in an isolated system where heat and work are both absolutely zero, the internal energy never ever changes. It remains completely constant.
But here's where we have to take a pretty sharp turn into reality. Because real-world chemistry almost never happens in a rigid, sealed, bomb-like container where volume is perfectly fixed. If you're in a lab, you're probably mixing liquids in an open beaker, and that beaker is sitting right under the constant heavy pressure of the Earth's atmosphere. Why does this matter? Well, because if your reaction produces a gas, it has to physically push the atmosphere out of the way to expand. And pushing the atmosphere out of the way actually requires the system to do work.
And that leads perfectly into our final section, Part 5, Introducing Enthalpy in Real-World Chemistry.
To solve this messy open-air reality, chemists use an incredibly elegant mathematical tool called enthalpy, which is represented by the letter H. Enthalpy is defined as the system's internal energy, U, plus its pressure times its volume. By cleverly bundling pressure and volume right into the very definition, scientists created a tool that automatically accounts for the energy spent pushing the atmosphere out of the way. Now, what's really interesting about this is just how simple it becomes. Thanks to the way enthalpy is defined, if a reaction happens at a constant atmospheric pressure, the change in enthalpy, delta H, simplifies entirely down to just the heat absorbed or released. You don't have to worry about calculating any mechanical expansion. You literally just stick a thermometer into the beaker, measure the heat exchange, and boom, you have your answer. It is an absolute game changer and a massive practical relief for chemists everywhere.
And this gives us a brilliant, straightforward way to categorize chemical reactions. If a reaction has a negative delta H, it means the system lost enthalpy by evolving heat out into the surroundings. We call this exothermic, like a burning fire. On the flip side, if a reaction has a positive delta H, it gained enthalpy by absorbing heat from the surroundings. We call this endothermic, like an ice pack turning cold in your hand.
So we've successfully mapped some of the core rules of the universe. We know energy is simply transformed, it's conserved, and it's transferred between a system and its surroundings as heat and work. But honestly, this leaves us with a profound, lingering question. If energy is always perfectly conserved overall, why do reactions happen at all? Think about it. What actually drives a spark to turn methane and oxygen into a roaring fire, rather than everything just sitting there doing absolutely nothing? Well, the answer to that question requires us to go beyond just energy. It requires us to explore the mind-bending concepts of spontaneity and entropy. But that's a fascinating puzzle for our next explainer. Thanks so much for watching.